So now let's take a look at section module 4.2. We're going to be comparing linear and exponential behavior. So we'll be going through some of the lesson parts from the MAT AS, and we'll briefly take a look at a few of these slides. So what I'm going to do is just highlight a few things. So we've got two products. Both of them are selling for $300. So there's an iTech device and a Dana Systems device. Each are selling for $300. But what happens is there's a difference in how their value decreases. The iTech device will decrease by 30% each year, whereas the Dana Systems device will decrease by $45 per year. So that's a set amount versus a percent amount. And we're going to see that's really what makes the difference between a linear equation, an amount of change, and an exponential, a percent change. So we'll look at a few examples here, a few steps into this process. So we're going to skip over these questions. This is what we want to see. So first of all, we know they both start out at 300. So this was the iTech device that is going to drop in 30% of value. So we could actually multiply that by 70%, because think about it. You lose 30% means you retain 70%. And that's the key part of thinking exponentially. We're thinking 100% is no change. You get 100% back, you still have what you started. There's no change. It's not exponential, it's not linear, it's no change. If you're decreasing, you're getting less than 100% back. But typically in our world, if you go shopping, you get a 30% off, right? Well, the best way to calculate what it will cost you is to think about the 70% on, right? 30% off, 70% on. You pay 70%. So the math is 30% times 70%. And so each year we're going to multiply by 0.7. It's going to reduce by 30%. And we see that happening. 3 times 7 is 21, and then so forth and so on. But notice the amount of change actually goes down. It's, because it's a percentage. Once we have a lower amount, 30% of that lower amount is less. So the amount of change in any given year is different from year to year. The percent amount of the change remains the same. That's exponential. Now over on the Dana System side, that's going to be a linear change, a change by $45 each year. So it's maybe a little easier to think about. We're going to subtract $45 each year, right? And so that gives us a setup like this, $45 coming down. We end up in both cases, at least in year 6, at about the same value, relatively speaking. But notice how it changed differently. Okay, the percentage change dropped quicker in the first few years, and then since you're taking 30% of a lower amount, it sort of slows down. If you look at the amount of change, it's right here at about between year 2 and 3. The change was about the same, $45 versus $45, and then after that, the exponential changes actually, as far as being an amount, is less, right? It was greater at the beginning and then less at the end. So that's how a decreasing exponential function works. And let's see, I think there's going to be a graph, so we're going to go through to that. Well, this is the function we were talking about, right? So for an exponential function, here is the y-intercept, the starting value. We're going to see that we will categorize that as a generalized function, f of t, or y, right? Y equals a, that's the starting value, times the base raised to the exponent. What we're going to see is that the exponent is the number of years. Okay, and what we see for the value of the base, that that is in relation to 100%. So if it's below 100%, this case 70%, then it is a decrease. If it's above 100%, then we're increasing. Okay. And then we compare that to linear, which are functions such as y equals mx plus b. Notice the difference in the b. In this case, m is our rate of change. It's the amount of change, $45, and it's negative in this case. And the b is representing the y-intercept here. So it's not that b is always the y-intercept. It's just in this case. In the linear case, we use b for it. In the exponential case, b stands for base, which is actually the rate of change, or incorporates the rate of change, right? This is not a 70% rate of change. We have to think in terms of 100. It is a 30% decrease. All right, I think that's good for the PowerPoint. So we're going to freeze up here for just a moment. Okay, there we are. We're back, and let's go into the lesson. So let me back up just a little bit, because I want to show I've adjusted the iMath AS. You'll notice there is no longer the calendar to see how things are progressing, when things are, quote, due, when you should have them done. I'm going to have you refer back to Canvas. All right, here's Canvas. And yeah, I did introduce this in class on Monday, but just want to make sure everyone is aware as we get to the second exam content. There is this learning schedule, and it's also embedded into the modules. So you can see on Wednesday we're doing 928. That's when we're doing 4.2, 3, and 4. So if you click, closed it, click on the learning schedule. This is the important part. This is what's going to drive, this is where your calendar is now. This is what's going to drive, hopefully, your decisions as far as when to get things done. You're going to see I put all the due date down here. Everything's due by the exam date. That does not mean that you should try to get it all done on the night before the exam. I couldn't see that being possible. This is 4 weeks worth of work to learn, and you need to do it on a regular basis. But I'm giving you the agency to make those decisions. Something comes up in another class, I understand, but you've got to get on and you've got to make the adjustments so that you're able to keep up with the schedule. Yeah, can you wait and maybe do a makeup here? Certainly. But if you keep on track with this, it'll be less stress for you as you learn, and then it's easier to answer your questions as we go. As you see, we're covering over 3 different chapters, so 4, 5, and 6. All right. So let's get back to the Math AS. And so what you'll see is each of the modules are here, and now we are in module 4, so you'll want to click on that, and that will expand it. And then you can see all the modules we're going to do. So there was module 4 we did on Monday, or 4.1. We're now going to take a look at 4.2. There are both the lessons and the homeworks. The lessons have no due dates, as we've discussed. Those are open for you to review, and those are what I'm going to use for much of the lecture, going through the examples. And then you're responsible for getting the homework done. Notice it does have a due date of 10/26. Again, that doesn't mean to sit back and wait until 10/25. It should be done this week as we move forward. And of course, you might be listening to this at some other time, but yes, it needs to be completed. So let's take a look, this comparison of exponential growth to linear. And the first thing we're going to do is look at a hurricane relief fund, which is very appropriate. This morning I'm watching the news in the Florida, the Ian hitting the Florida coast. So basically we're going to look at how a exponential function actually works. So who is this? This is Bob. He's setting up a relief fund, and he got a $35 donation. He's got $35. The next day he's got 3 times as much. So at the end of the first day, amount has been tripled. So we're count this the first day. So $35 is the beginning of value, and then he keeps tripling, which is great. So that means when we triple, we multiply by 3. So we could fill out this table as we go, multiplying by 3 each time. And again, it's going to make me sign in. Just a moment. Okay, so 105 times 3 is going to be 315. This gets multiplied by 3. Right, we're multiplying by 3. We're multiplying by 3. We're going to multiply by 3, and then multiply by 3. Okay, and there's a video that sort of walks you through this, so I'm going to post that one. They do a pretty good job of working through these questions. It's about a 6-minute video, so we'll let you take a look at that. What I want to focus on is to add something new, and what we come up with is, as we were saying, they're saying coming up with a function. So what's happening here, our donation function is we started with $35, and then we are tripling it. Now, they don't give us a percentage, so we don't have to think in terms of 100%, but to triple something is to multiply it by 3. Each time we're multiplying it by 3, so that will be the exponent. So there's our function. I'm going to do this with Desmos to show you how you can graph it. And again, while you will be using your handheld calculator, or actually I do have my TI calculator, why don't I go ahead and show you how it would work with this. Okay, there's another one I'll show you with Desmos because we won't be doing it as much. So y equals 35, oops, right here, 35 times 3, and I like to put it in parentheses, and we're going to put an exponent, and so the exponent key is right here. Raise it to the x power. Okay, so I'm going to hit enter. And we want to see this graph, so I'm going to graph it. As soon as we get there, we probably won't see enough, because usually a graph goes from -10 to 10. This one doesn't look like. I'll go standard. The standard view is a window that we don't really see much, right? Because we know our first day, or the y-intercept, is at 35. We don't see to 35, we only see to 10. So one of the things we have to do with this is we have to change our window. Now this is going to give us -10 to 10 days. I think we're okay to start at 0, right? And go 10 days is fine. Actually, all we're going out is 7 days. But what we need to anticipate, though, is our output. How big does it get? And if you look at the table that they've come up with, the donations actually get pretty big. So I'm going to go to $5,000 just to be on the safe side. But this is kind of, you have to anticipate where you're going, and it's sometimes kind of a guess and check type thing. So we'll enter there, we're going to graph it, and yes, indeed, we now see how things are working. If I want to find out what is the y value after 7 days, actually 1, 2, 3, 4, 5, 6, 7. Actually, we're not going to be able to see that. It's more than 5,000, isn't it? Or I did 500. What did I do? Let me go back to my window. I did 5,000. Maybe I need to do like 50,000. Let's put in another 0 here. And let's see how that looks on the graph. Wow. Yeah, we got to get up about 50,000. So I want to find out what is the value when x is 7. So there is a tool in here. It's under calc, and calc is in blue, so we go second, calc, value. We're going to ask for the value, and it asks us what x value we want. We're going to put 7 and enter, and it's going to jump to that. Let's see, 35 times 3 raised to the x power, $76,000. That's amazing. Just making sure I got everything right. I wasn't expecting that, but that's, so after 7 days, we've got 76,000, and that's what happens with this repeated tripling. Exponential functions can grow very, very quickly. Notice I only went to 50,000. I thought that would be enough, but I probably should have gone to 100,000. Then I would see that little dot there, but I'm able to get my answer. So as we come back here, we're actually able to answer what is f of 7. Well, we just found out it was 78,000 something, right? Where's my 70 or 76,545? Now, and I was thinking maybe because they do this inverse thing, they want to know how many days, right? Use it to find out this inverse, which is the question really it's asking is how many days does it take to raise $2,835? Well, we already know it's less than 7. So let's go ahead and take a look. We can do the same thing, realizing that this 2835, that it is a y value. So the way we approach that is we actually enter another function, y equals 2835. And what that's going to give us is a horizontal line, and where it intersects our graph, that's going to be our answer. Enter that. It's going to be in red. We're going to graph it. It's way down here. And then we just need to find this intersection. And again, there's another tool. You might have seen it last time. It's the calc tool. So graphing and using these calc tools, intersect number 5. Now, the way we use the intersect tool is it asks for which is the first curve. So notice it's on the green curve. I'm going to hit enter. Enter, not on. I'm going to hit enter. Then it jumps to a second curve and says, is this the second curve? And I have to say, yes, that's the second curve. It asks me to make a guess, and I'm already close enough to the intersection, but sometimes you may need to move it, and if you need to, you can move it left or right. So I'll take a guess, get closer to the intersection point, and hit enter. And it tells us after the 4th day is when it's 2,835, right? X equals 4. So this is a way you can really solve any equation, having the y solving for x. So now we're able to answer that question. Okay, so the inverse of this is going to be 4. And what we found is that after 4 days, there's 2,835. Okay, and you can answer those questions. What I want to show you is they do graph each of these. Maybe I should have looked. So we've got 0, 1, 2, 3, 4 days, 5 days, and you can see it follows along a J-shaped, sort of a J-shaped curve, and these are following a tripling pattern, right? They're tripling each time because they're being raised to the 3rd power. If you wanted to represent that change as a percentage, let's come back to here. Remember thinking that 100% is no change. So what would, we've got our function 35, 3 raised to the x power. That's our function, right? What we do is we take the input value, make it into a percentage. 3 times 100 is 300%. But it's not a 300% increase. What it is we have to subtract the 100%, because remember, that's the basis. We're getting back what we started with. And we're getting the increase is actually going to be a 200% increase. So anytime we have a 200% increase, that means we're tripling. But mentally, a lot of times we'll think, oh, that means we're doubling, right? 200, we're getting 200% bigger. But that's the amount of the increase. The amount that we had to start with is still there. So we've got that 100 plus the 200%. Okay. So let's kind of keep going through this. And notice there is this embedded video. I've got that also, since it's a YouTube one, I've got the link to it in Canvas, so you can watch it directly from there. So this will be an overview video, and these other videos, if I can embed them, I'll have them there. If they are not a YouTube video, then I can't. I would have to download them, and so anyway, I'll leave them here. So I'll let you know about those. And again, this is getting back to letting us know that as we get the rate of change for an exponential, it is because it's percentage. Remember, with percentages, we had ratios, right? One thing we looked at is over of. If you watch the video, equals percent over 100. So we could set up these kind of ratios. Also, we could think of this is and of, because a lot of times that's the language that's used in percent problems. We could also think of it as part. This is the part, partial, and this in the bottom would be the whole. So the whole represents 100%. The part of that is the percentage. And again, sometimes the percent itself could be over 100 if we're increasing. So we keep that in mind. But when we want to see the difference between any the factor that comes up, we need to be dealing with next door neighbors. So this, what happened in the first day and the second day, so they have to be right together. You can't take the ratio of what happened at the beginning and 4 days later. It's not going to work for an exponential. So these are taking the y values, and again, we can actually multiply. That gives us, and when you do this with this, like the last one we did, you would take the second day divided by the first day, you'll get 3. And the same thing, if you take the first day divided by the beginning day, you'll get 3 on that hurricane problem. So it just depends. So both of these are ratios we can use. Okay, so it's the y values of consecutive days will give us a factor. And what do they do? That factor gives us the part of the exponential equation that gives us the rate, right? It gives us the b. This is actually going to be equal to b. And then a is whatever we started with. This is an exponential function. Starting value times the factor of change, again, raised to a power, and then we can multiply out. Okay. When we have linear change, we see that that's going to give us a straight line change. So we've already worked with this, but I'll let you take a look at that in the lessons. It'll connect you to what we're doing in the homework. Okay. And some of these. Okay. When we start to get exponential, we know it's exponential because we start to see a curve. Even if it's a slight curve, we see this is not a straight line, it's curving. And so we know the model is not linear. Okay. And that's, again, you go through and you do the calculations, you get all the numbers, and then you can graph them. Now there's a way to do that with the TI calculator, and we will get to that probably later in another lesson. Okay. So here's an example, and again, I encourage you to kind of look through these. You'll have it is a decreasing, so the coffee milligrams of caffeine is going down exponentially, and so this is going to be a percentage below 100, right? So in this case, after you drink your cup of coffee, you reduced the amount of caffeine that was initially there by 74.9%. 74.9% of the amount at the beginning of that hour. So this is what's left over. What we want to think about is how much is decreasing while you subtract it from 100%. 74.9, and what we'll get is the rate of decrease. 74.9 is what we're getting back. So to get the rate of decrease, we have to go this route, and then we get 0.1. 4 from 9 is going to give us 5, and 7 from 9 gives us 2. So 25.1% decrease. Okay. Another video, and again, this is a YouTube one, so it will also be posted in Canvas. And they take you step by step through that particular one. And so that's the end of this lesson. This will get you started. Take a look at the 2 other videos, the specifics, and then get into the homework, and we'll work through this together.